Hello friends. In this video I want to talk about a basic but important aspect, such as electrical distribution schemes and their protection against indirect contacts. My name is Robert and I hope this video is of interest to you. In this case, do not forget to drop a like, subscribe to this channel and activate the notification bell. In general, the electrical voltages that we use in our homes, or in small and medium-sized companies, are considered as low voltage. They are voltages of less than 1000 volts AC, for example 230 volts between phase and neutral if we consider a single-phase system, or 400 volts between phase and phase for a three-phase system. But given that the voltage used in transmission networks can reach up to 400,000 volts, this implies that there must be several stages to reduce this voltage to that of use. This is achieved in a first step in the substations and finally in the transformation centers that we can see in our neighborhoods or industrial areas. In these transformation centers, a transformer reduces the voltage from, for example 30 kilovolts, to the 400 volts AC, that we have mentioned. From the transformation center, the electrical energy will be transported to the users through three-phase lines made up of 3 cables for each of the 3 phases, and an additional neutral cable so that we will be able to supply three-phase loads such as motors, or single-phase such as computers. However, in this electrical scheme, 2 fundamental aspects need to be mentioned that undoubtedly affect the safety of the facilities: on the one hand, the earthing of the transformation center, and on the other hand the type of grounding of the masses of the metal casings of the loads in the user's facilities. And precisely these 2 aspects will define the different electrical distribution schemes defined by the International Standard IEC 60364. We can name the different distribution schemes using a multi-letter system. The first letter is associated with the type of earth connection of the network, normally in the transformer of the transformation center, although it can also be complemented in other points. The second letter is associated with the type of connection of the masses of the loads such as electrical machines. In this way, for the first letter we have the following options. We use the letter T, if there is a direct connection to earth in the transformation center, normally the neutral tap of the transformer. We use the letter I, if the active parts of the installation are isolated from ground, or if there is a connection point through a high impedance. Therefore, T, if the power supply is grounded directly, and on the other hand, I, if it is connected with an impedance or isolated, that is, an infinite impedance. With this word game you can easily remember it. And for the second letter, that is, the one that indicates the type of connection in relation to ground of the masses of the customer's loads, that is, their metal enclosures, we use the letter T, if these are connected directly to a ground independent of the one of the distribution system. The second letter can also take the value, N, in case the masses of the loads are connected directly to the grounded point of the transformer, which for a 3-phase installation, as we have said, is normally the neutral. Additionally, in this second case, we can add a third letter that can take 2 values. The first option is the letter S, in which case 2 conductors arrive at the customer's loads, one the neutral and the other to connect the masses of the loads, which is called the protective earth PE. It is easy to remember this type of connection if we consider the letter S, associated with separate lines. The second option would be the letter C, and it is used to indicate that only one line is used, that simultaneously acts as neutral and connecting the masses. In this case the letter C, we would associate it to a common line. We can also have electrical systems where both schemes coexist. Therefore, S, if they are separate lines, and C, if it is only a common line. Again, with this word game it is very easy to remember. In this way we can combine these letters to obtain the following schemes. Scheme TN, in a TN system, the neutral of the supply is connected to earth directly, while the masses of the receiving loads are connected to the same earth connection of the neutral. The electrical diagrams TN can be divided into 3 types depending on whether the neutral and the protective conductor are separated or not. TNS diagram. In this diagram we see the neutral of the supply grounded, and from that point 2 conductors come out that reach the receiving installation, one that acts as a neutral and we call it with the letter N, and the other that acts as a protective conductor and we name it with the letters PE. TNC diagram. In this other diagram we see that the neutral is also grounded, but from this point only one conductor is delivered, that will be the one that reaches the receiving installation and will act as both a neutral and a protective conductor, so it we denominate by the letters PEN. Scheme TNCS. In this case, a single PEN conductor will arrive in some part of the installation, and in others it will be divided into two conductors, one for neutral and the other for protection. Under normal conditions with the protection switches closed, a current lower than the nominal of the installation will circulate, and the leakage currents through the protection conductor will be minimal. In the event of a fault between two phases, the loop that is formed will basically consist of the active cables and the transformer coil, so its impedance will be very small, and in this case a high current will be generated. Remember Ohm's law, which tells us that the current is equal to the voltage divided by the resistance, so the smaller the resistance of the loop, the higher the current that appears. In this case we are talking about short-circuit currents. This very high current must be detected and interrupted by the protection against overcurrents and short circuits, whose function falls on the fuses and circuit breaker protections. In the event of an indirect contact in the receiving installation, for example, due to an insulation problem of an active cable inside a machine, a contact occurs between a phase and the ground of the receiving installation. In this situation, the fault loop we have is made up of the phase conductors and the protective conductor PE, or PEN, and the transformer winding, so its impedance is very small, giving rise to the appearance of a high short-circuit current that does not involve the earth electrode of the supply. In this case the protection against indirect contacts is carried out by means of the appropriate choice of the activation curve of the protections against overcurrents and short circuits, that is to say, circuit breakers and fuses. In these cases, the protection trip must be guaranteed before a specified maximum time has elapsed, in accordance with international regulations. If in a TNS system, the disconnection time cannot be guaranteed by means of the overcurrent protections, differential protections may be used. In a TNC system, no differentials are used. Scheme TT. In this type of scheme, both the power supply and the masses of the receiving loads are connected to earth directly, but they are different earths, for example, the transformer earth of the transformation center and the ground of our house. These grounds are physically and electrically separated and use different stakes. In this type of scheme we will find two types of protections at a functional level, on the one hand, protections against overcurrents and short circuits, and on the other hand, differential protections. These two protection functions may be physically implemented either in a single element or in two separate elements. Under normal conditions with the protection switches closed, a current lower than the nominal of the installation will flow and the earth leakage currents will be relatively small. In the event of a fault between two phases, the loop that is formed will basically consist of the active cables and the transformer coil, so its impedance will be very small, and in this case a high current will be generated. Remember again Ohm's law, which tells us that the current is equal to the voltage divided by the resistance, so the smaller the resistance of the loop, the higher the current that appears. In this case we are talking about short-circuit currents. This high current must be detected and broke by the protection against overcurrents and short circuits, which falls on the fuses and circuit breaker protections, although as I have mentioned we can have combined protection systems. If these two elements are separated, so that the differential is not damaged, the short circuit current of the differential must be greater than that of the circuit breaker. In this sense, we must differentiate two different concepts, such as the maximum current that the protection supports, and on the other hand, the breaking current that a protection can withstand when opening its contacts. As I have commented, under normal conditions the earth leakage current will be relatively small. However, in the event of a fault between a phase and the ground of an equipment, the current that appears to ground will normally have a lower value than the short-circuit current. In this case, the fault loop that we have, in addition to including metallic conductors such as the phase conductor and the transformer winding, also includes grounding resistors, which may have a more or less high value depending on the state of the stakes, whether it is summer or winter, etc. In this way, the resistance of the ground loop is not as low as the resistance of the short-circuit loop of active lines, but the currents that appear can be enough to cause the metal chassis of a load to be put at a dangerous voltage. The fault voltage to which the equipment casing is subjected will be equal to the product of the resistance of the protection cable, plus the grounding resistance multiplied by the fault current. In this type of scheme, it is possible that the protections against overcurrents and short circuits do not guarantee the protection against ground faults due to a high impedance of the ground loop, so it is necessary to use differential switches, so that either themselves or through the associated circuit breakers, they cause the automatic opening of the installation when the earth leakage current exceeds a predetermined value. In the case of the 30 mA differentials used in homes, its reduced current and its opening speed will also serve as protection against direct contacts downstream of the differential. If the installation works at 230 volts and we consider a body resistance of about 1000 ohms, then, if we did not have the 30 mA differential installed, the earth leakage current through the body would be about 230 mA, enough current to cause problems if the current is not interrupted in time. Fortunately for this person, the differential will interrupt the current in less time than it would take to enter the dangerous zones represented in blue and red in the graph shown according to the IEC 479-1 standard. Since RCDs prevent the existence of high earth fault currents, they not only reduce the risk in the event of direct or indirect electrical contact by people, but also reduce the possibility of fires due to electrical defects by minimizing electrical energy put into play during a failure. The TT system is one of the most widely used in electrical installations in Europe, both for its cost and for its protection features for people. Finally, we have the IT system. The first letter, the I, indicates that the active elements of the supply are isolated from ground, that is, they do not have any direct connection to ground. The second letter, T, indicates that the masses of the receiving facility are directly grounded. In this type of installation, it is recommended not to distribute the neutral. Under normal operating conditions, the earth leakage currents will be minimal given the impossibility of returning to the supply transformer, given its lack of connection to earth, which undoubtedly implies a very high impedance loop. In the event that the receiving installation has a fault, and a phase makes contact with the metallic envelope of an equipment, the current to ground that appears continues to be low, given the high impedance between the supply and ground, so the voltage appearing on the metallic chassis of an equipment with respect to the ground will also be small. In these cases, if a person touches the conductive casing of an equipment, he will not be in a dangerous situation and will not experience any electric shock, and the current through the body will be imperceptible. For this reason, it is said that this type of scheme supports a first defect between phase and mass, which makes it used in critical applications where it is necessary to ensure service continuity, such as in operating rooms and hospital intervention rooms. These IT scheme areas are normally generated from another scheme using special isolation transformers. In this type of installation, an installation monitoring device constantly monitors the installation, causing an audible or visual alarm in the event of a first installation failure, but allowing the continuity of the installation, being mandatory to locate and eliminate the first installation failure. In this way, life support teams in an operating room can continue to work during a patient intervention, even with a first failure. Residual current devices or RCDs are not used in this type of IT installations generated by an isolation transformer. A second failure of another phase with a metallic envelope would cause a short across the chassis between the two failed phases, which will cause the overcurrent and short circuit protection to trip. Each distribution scheme that we have seen has its advantages and disadvantages. For example, the TN system implies a lower cost in electrical protections, but requires an adequate selection of protections and it offers a lower protection against fire. The TT system offers high protection of people, of the installation's own loads, and against fires, but it requires a greater surveillance of the grounds and verification of the correct operation of the differential protections. Finally, the IT system has the advantage of offering high availability and fire protection, but they cannot be too extensive, and usually require insulation monitoring devices. And so we have reached the end of this presentation that I hope has been of interest to you. If so, don't forget to drop a like, so that I know that you liked it. In future videos we will see more in depth the differential protections and especially how to verify them so that the installations with the TT scheme are really protected. Therefore, if you don't want to miss them, don't forget to subscribe to this channel and activate the notification bell. See you in a next video. Bye.